Professor Dennis Meadows is, as many know, Professor Emeritus at the University of New Hampshire, where he was director of the Institute for Policy and Social Science Research. He co-authored the pioneering 1972 report, The Limits to Growth, which analyzed the long-term consequences of unconstrained resource consumption driven by population and economic growth on a finite planet. From 70 to 72 at Massachusetts Institute of Technology, he was the director of the Club de Rome project on the predicament of mankind. He has been the director of 3 university research institutes, first at MIT, then at Dartmouth College, and finally at the University of New Hampshire, where he is, as I said, emeritus now. He is the past president of the International System Dynamics Society and the International Simulation and Games Association. He has facilitated workshops and developed innovative and complex strategic games all over the world for decades. He has been a corporate board member and a consultant for governments, industries, the nonprofit groups in the US and in many countries around the world. He co-founded the Balaton Group in 1982, an international network of over 300 professionals in over 30 countries involved in system science, public policy, and sustained development. He has received numerous international awards for his work, including the prestigious Japan Prize in 2009. So he will now give his talk, which he entitled Cognitive Challenges of Modeling Long-Term Climate Change Dynamics. So Professor Meadows, we're very honored to have you with us in this summer school and in this morning workshop. So if you please.
Thank you very much, Serge. And let me thank also Professor Lejeune, who 2 years ago wrote me the first time asking if I would come up to participate in the summer session. I view global problems as being very strongly a matter of cognition. And so I thought it would be great fun to do it. I'm only unhappy that the pandemic intervened and that instead of visiting again beautiful Montreal and meeting you personally, I have to do this from my home. But I'll do my best to be helpful. And I intend to sit in on most of the rest of the session. So 50 years ago, I directed at MIT a research team which built computer models to understand long-term causes and consequences of growth on the planet. And that produced many publications and reports, including, of course, the Limits to Growth, which came out in 1972. Since then, I've been in many, many countries talking with people, trying to help them understand the long-term problems that we face on a finite planet. Initially, climate change was not a central focus of our work. Actually, I went back recently and counted in the 1972 report how often the term climate change even was mentioned. And it was, I think, one time. We used CO2 emissions in that report simply to illustrate the exponential growth of a pollution. We didn't trace that growth of that pollution to the consequences that we talk about now. But in trying to communicate the problems of limits to growth to people and bring them to understand and to change behavior, we ran into the same issues which now we find in talking with climate skeptics. After 40 years of trying to present research graphs and data and finding that it basically didn't change the opinion of many people, I shifted over to what I call games, the topic which I'll be discussing today, of course. And there I began to see the possibility to help people get a new understanding. So more recently, we've moved from natural resource issues over to climate change. And I will share with you today, first of all, in this 2-hour topic, and then again tomorrow morning briefly, some of the insights and ideas that we have developed. So first, let me just pause for a moment and share my screen and repeat what Robert said. After the 21st slide, roughly halfway through my session, I will stop the formal talk and take questions, any uncertainties, anything I haven't explained very well, etc. And then after a few minutes of doing that, I'll go back into some additional formal material. Let me say, I put together a group of 40 slides, which include many videos. There are a lot of ideas on those slides, and you could, of course, sit there and take notes if they seem interesting, but I suggest something different. On my first slide is my email address. Simply write me an email message and ask for the slides. I'll be happy to send them to you. And then you'll have them for your own use. In some cases, the slides help you to run a game. In other, they explain theoretical concepts, or they tell you where in a book or in on the web you can find more information. And I will be happy to send them to you. Just note that the slides which you get won't have the videos in them because they take gigabytes of memory. Rather, I'll just paste in a picture. The videos themselves are available on the web, and the descriptions of my games are all available in a book. Okay, well, let's get into it. The cognitive challenges of climate change dynamics. Note here these issues. Dynamics, of course, means behavior patterns. And I'm going to be talking about how very simple games can be used by you. This is not an academic exercise. I intend to be giving you some useful tools, how they can be used by you to help others understand some of the things that concern you about climate change. You'll note this is in a way like a lecture about painting. I'm going to be showing you some techniques of sketches. I'll be illustrating some concepts like how to get different colors. But finally, at the end, it's up to you to decide how you want to use these. And probably very quickly, you'll start to use them in ways different than what you see me doing here. That's as it should be. My goals for this session are the following. First, I will list some of the difficulties in understanding climate change. Excuse me. And I'll describe the role of very simple games to help improve understanding. And I want to show you personally how you can use 9 different little games in your own efforts to communicate your understanding of climate change. I'm drawing from a book I wrote recently with some colleagues called the Climate Change Playbook. It lists 22 different exercises. All 9 of these are in that book. Note, I'm not going to prove to this group that climate change exists. I imagine that if you didn't think it existed, you wouldn't take the time to listen to this seminar. I'm not going to describe the causes of climate change. I expect others in this seminar will do that. And I'm not going to describe measures for reducing the harmful effects of climate change. Those are extremely important, but others in this seminar have more knowledge about that than I do. So I leave it to them. Now, when we say climate change, it means different things to different people. And as you'll see later, climate has not only physical, but social, economic, psychological and other consequences. But for the moment, let's use as an indicator of climate change some of the physical indicators. So for example, increasing average temperature. Generally around the world, as we all know, the temperature is going up, and the goals of the climate control group have been stated simply to stop the rising in temperature and hold it at something like 1.5 degrees above averages. So average temperature is one of the physical symptoms, but there are others. Of course, rising sea level. The sea level has gone up about 8 inches on average during this century, so for the past 100 years. Forecasts are uncertain, but they call for another 1 to 8 feet of sea level rise in the next 100 years. We see it already, greater variation in wind, temperature, precipitation, many more storms. I was just looking this morning at NASA's forecast for hurricane season, and they're calling for more storms this summer than we've had typically in the past. Not a great concern to you in Canada, but I can say down in the United States of some interest. The ocean is becoming more acidic, making, of course, difficulties for the life that needs to form calcium shells. And there's a declining ice cover. Now, climate change is all of these things, but for my purposes, just to keep things simple, I will stress increasing average temperature. We'll use that as a surrogate for climate change more generally. If you look at global temperature since about 1880 up to the present, so 140 years, you can see how each year's temperature globally has been either above or below the long-term average. And the trend is very clear. Global temperatures are increasing. And of course, already this spring, we're facing record high temperatures, at least in my part of the country. Now, this is going on despite the fact that the UN, United Nations Framework on Convention on Climate Change, met already about almost 30 years ago and got 165 different countries to formally sign that they were worried about climate change. They wanted to do something about climate change. Nonetheless, it just keeps getting worse and the pace is accelerating. So, interesting question, why is that? Well, of course, many reasons, but one of them, particularly relevant, I think, for this seminar, is that climate change is hard to understand. The process confronts us with all sorts of issues which human species hasn't evolved very well to understand. I list here 9 of them, not as an exhaustive list, but simply to provide a conceptual framework for my presentation this morning. Here's what I see as some of the cognitive challenges of climate change. Understanding climate change requires learning about ambiguous words. Climate change is by its nature a global problem. It means that people from many different cultures, many different primary languages are having to sit down and talk about it. Unfortunately, they often are forced to do it in English, which means already they are having difficulties going from their first language to English. And even in English, as we'll see, the words can be ambiguous. So you say one thing and somebody else understands something different. We have to learn how to deal with that. Another problem with climate change is the varying time constants. When you start to think about the way that causes and consequences of climate change appear, you see things happening in days, seasons, spring, summer, fall, winter, years, decades, centuries, millennia. And a concern or a policy which might work over days becomes totally irrelevant for centuries or millennia. We need to learn how to deal with that. There are different facts. Economists look at the financial side. Biologists look at species. Politicians may look at the agricultural sector. architects are trying to understand the physical parameters, such as sea level rise. So when these people sit down and start trying to talk about climate, they're of course all looking at a different set of facts. We need to understand how to do a better job with that. Differing perspectives. You look in different places. You look over different time. You're concerned about different groups. And when you all have to sit down and agree on something, it's a cognitive challenge. The process of exponential growth, something we focused on in our 1972 book, is very, very bewildering. It does things that we don't expect. And because climate change is inherently an exponential process, we need to do a better job of understanding it. Then there's the issue of short-term versus long-term. Some people are worried about winning the next election. Some people are worried about the life of their grandchildren. They're going, of course, to have difficulties in agreeing on what to be concerned about and what to do. Climate change is also difficult because it visits its costs and its impacts in different places at different times. I remember I was in the Soviet Union talking about climate change and saying they should be very concerned about growing temperatures. One of the participants was from Siberia, and he said, we think warmth will be a great thing, so bring on climate change. Of course, by only focusing on his part of the globe and over the short term, he therefore had a very different understanding about it. The rich countries are being asked to pay now for things which are going to benefit poor countries later. Politically, this can be a very difficult job, and so that's another challenge. Somebody once said you can't do only one thing. Well, climate change poses us with all sorts of interconnected consequences, and each of them has cognitive challenges. So I've tried to understand how simple games could open up people to this notion that doing one thing here may cause several things elsewhere. And finally, we have this problem that habits which we adopt just continue and are very difficult to change. So games can also be helpful in that. When we talk about learning how to do this, we should recognize that there are lots of different methods for learning. I'm sure those of you who are watching today have used and each of these, both for your own purposes and while watching others. There's lectures, of course, the university professor's favorite method, probably not very good actually, but very common. Reading, I often will sit down and read books on topics which are new to me and trying to help to understand them. In the early days, before there was writing, stories were the way that one generation helped the next generation to learn. Stories being told to convey culture, clever ideas, the notions of morality and story, and so forth. Group work, team projects, very useful way for learning how to do things, either as apprenticeships, as they do, for example, in Germany, or maybe in a class you do teamwork where each group works together. Very effective way of learning. Games, of course, the focus of what we're doing to be talking about today. Movies can be a way of learning about things. Not always, of course, but sometimes. Computer simulations are one of the things I use when I'm trying to learn about new things. Internships and filming films of things. Trying, as we've said, if you want to learn something, then teach it. And I think the same analogy would be for filming. If you want other people to see something, then figure out how to film it for yourself. But we'll be focusing on games. So what's a game? A game is an activity usually involving skill, knowledge, or chance, in which you follow fixed rules and try to win against an opponent or to solve a puzzle. And actually, when you're trying to solve a puzzle, there's an opponent, but it's you. Often you'll do this several times, hoping that in the process you learn how to do it. And you note here the key concepts are goal, competition, and activity. So let's quit being so theoretical about it, and let me illustrate very quickly a simple game that I've developed to help people understand the ambiguity of words. So I have here a piece of paper. I just picked it up out of my wastebasket. I ask everyone who's watching, reach into your wastebasket or onto your desk and pick up a piece of standard sized paper. In just a moment, I'm going to give you some instructions for using it. So I'm going to wait for 5 seconds while each of you out there gets a piece of paper. But make sure it doesn't have something on it you wish to keep, because in the course of this exercise, we will be destroying this paper. So I have in my mind an image of a specific shape for this piece of paper. I can see how it will look like after I'm finished working with it. Your goal is to take your piece of paper and make it resemble that shape which I have in my mind. So you take a piece of paper in your hands and please follow my instructions. When I'm doing this in person, I'll ask that you don't ask questions. Now, of course, you're all on mute, so you can't anyway. And then just do as I tell you. Okay, let's see. So fold your paper in half. And tear off the upper right-hand corner. Perfect. Now, fold it in half again. Tear off the upper left-hand corner. Tear it, put it in half again. Tear off the lower right-hand corner. So you're all smart, you're all eager to follow the rules and achieve the goal. You've listened to my instructions, and so we should all have the same shape of paper. Open it up and see how it looks. Now, I will come back during the question period and see what was your experience. Notice whether you ended up with something like this or something quite different. One of the problems with games, even an incredibly simple, trivial one like this, is that they're so much fun that there's a strong social pressure to take whatever time's available, whether you're a teacher or a team making a plan or whatever, and take all that time and use it in actually playing in the game. That's a serious mistake, because discussing the game afterwards and drawing lessons out of it is an absolutely essential part of the exercise. Debriefing, which is what we call discussing afterwards, it gives each player an opportunity to identify what they did well and what they did poorly. That's why during the question period, I'll come back to ask, did you succeed in making your paper look like mine, or did it look like something else? It lets people talk about the process and refine their own understanding about what happened and what it caused. Debriefing can draw out some more general lessons. the amount of time that tearing up a piece of paper is going to be helpful to you in your future life is very limited. But there are some general lessons to be learned from the process, which are applicable very widely, and of course, especially in connection with climate change. Debriefing lets you draw out those lessons. It can bring you around to focusing on positive change. And finally, and this is for me very important, in the process of the discussion, hopefully you can get people to make some kind of commitment to doing something as a result of what they've learned. As I'll state in the future, changing somebody's understanding is of relatively little use, if at least in connection with climate change, unless it causes them to change their behavior. I don't care if you understand climate change better. I only care if you start to behave in a way that's going to make it less of a problem. In the case of the paper tear debrief, normally when I do this, I would be working with you in the audience and we would be engaged in a one-on-one conversation. Obviously, I can't do that over Zoom, especially when you're all muted. So I'm just going to walk down through this paper tear debrief very quickly. We'll come back to it during the question period. So what happened in this exercise? Typically, at the end of the exercise, I ask everybody in the room, 30 or 40 people in the room, to hold up their piece of paper. And there will be a half a dozen different general shapes. Looking around the room and understanding how differently people interpreted and executed a very simple set of instructions is often pretty funny, and it's a kind of an aha moment for people to see. You know, I mean, some of you out there right now are professors. Just imagine if in the process of using simple terms like left, right, and tear, I ended up with such an incredibly different set of images on paper. What could you imagine is going to happen when you start giving an hour-long lecture on climate change? Just think about all the different images that are going to be in the minds of the people who listen to it. We often see this kind of result in real life, where one person tries to communicate something that's very clear and real to them, but in the process, put into the minds of the listeners something very different. We see that with climate change all the time. Somebody will cite an example of something that they believe proves there is climate change, and a listener will take it as an example of the fact that there, in fact, isn't climate change. What characteristics of this paper tear exercise produced this result? Well, now we get back into the important lessons. I engaged in what we call one-way communication. I told you, don't ask questions, just listen to what I say. And that automatically sets up a situation where people are going to make mistakes or where there's uncertainty and they don't have a chance to resolve it. Climate discussions need to be interactive in order to be effective. Do those characteristics often arise in real life? Yes, all the time. I, as a professor, often have been surprised after giving a lecture, which I thought did an extremely convincing job of proving something, to have people come up afterwards and then make a statement which indicates they had a totally different impression from my remarks. I remember actually making a lecture in Montebello outside of Ontario, Quebec, in some time ago, about the limits to growth and global modeling. And I showed a bunch of computer scenarios to illustrate different aspects of exponential growth and limits. And afterwards, one of the participants came up, and the only insight that they'd gotten from my lecture was that the colors I used on to differentiate my slide results were very pleasing. And they were so happy about my lecture because I've been using such pleasing colors, something totally remote from what I've been trying to do. An interesting exercise, which I won't go through now, but I can recommend to you with this very simple game, is once you've done it with a group and people look around and see that they didn't do a very good job of producing the same results, ask them how they could rerun the exercise to do it better. And then actually appoint somebody in the audience to come up and run the exercise again, using the new rules to see whether or not they actually work. And then the key thing is to look for counterparts of those changes, which you can take back into real life to become more effective. This debriefing is part of a kind of generic cycle. I'm just going to restate again what we just did, because whenever you're running some sort of exercise, it's important to go through this stage. First, what happened in the game? And then, do those things happen also in real life? Games, especially simple short games, are so abstract, it's easy for people to consider that they have no relevance to real life. And it's important to sit down and specifically understand how things happening in the game also are happening in real life. Did you find those characteristics in real life that caused the changes in the game? And with those characteristics, could you change the game to make it have better results? So it's, you see, it's just going back and forth between the game experience, which people have actually lived in, and the real world experience, and trying to find analogs and metaphors in the game that are appropriate for real life. It's especially important for climate change because climate change involves very long-term processes. And it's, most people can't imagine that they will be around even for the full extent of climate change. If you can encapsulate some of those behaviors in a short game and then effectively make the transition to real life, it helps people better understand. What would be the counterpart for those changes in real life? How would you actually do vis-a-vis climate change to help out? And then getting a commitment to do it. Okay. So for each of the 9 problems in cognition, ambiguous words, varying time constants, and so forth, I've come up with a simple game. We just did paper tear as a way of helping to understand ambiguous words. Balancing tubes, as you'll see in a moment, helps people to start thinking about varying time constants. Frames, which I'll illustrate with a video, shows why people have a perspective on different facts, and so forth and so on. Circles in the air, paper fold. In red, I have put the names of the games, which, as they appear in the book I wrote called the Systems Thinking Playbook, or I'm sorry, the Climate Change Playbook. The Climate Change Playbook is a little pamphlet written by myself and 2 co-authors, Linda Booth Sweeney and Jillian Martin. It describes 22 games. It's available from Chelsea Green Publishing, and the reasons for it are in the other text assignment, which I made this morning, the chapter 4 from Dennis Meadows' book, Description of Systems. These are 2 official publications available for sale. For those of you for whom the price of the book is high, I'll just tell you that if you go on the web and type in free download Climate Change Playbook or free download Thinking in Systems, you'll come to a site where it's possible to download the entire text for free. It's illegal to do that, and I think it's immoral, but it's possible. And I just wanted to make it clear that those of you interested in following this up, but unable to or unwilling to pay for the book, still have access to it. I'll just note that in the case of the climate change playbook, the illegal version was something that we gave to the German Foreign Aid Agency long ago for use in their workshops. One of their members in, I think, South Vietnam or Vietnam now, scanned it and put it on the web without our permission. It's pretty good. It's about 95% correct. We've made some changes, improved our techniques, eliminated a few errors, but as a practical matter, not a bad way to get started. All of the games I'm using today also are illustrated in a workshop that I gave at Uppsala University in Sweden a couple years ago. I have put here the links to 2 YouTube videos, each a 2-hour segment. And listed below are the names of the games. So Paper Tear is sitting there. And that means that at this website, at minute 13, you'll see me running Paper Tear. At minute 53, I'm doing hands down, which I call secret code in this today, and so forth, and also here. The way I run those games is in no way an optimum or only option, but it's often helpful if you want to try it for yourself to see somebody else doing it first, and this shows you how to do it. The videos that I show today are taken from these websites. And as I said, if you ask me for the slides, I'll simply take them out because they're very large. But all the rest of the material will be in the slides. I like games because they provide learning by doing. There's an old saying, when I hear, I forget. When I see, I remember. When I do, I understand. Games are learning by doing. There's just something about embedding a lesson into a motor cognitive process, which makes it much more durable and useful to you. I'm using extremely simple games today. Games in general can go from 1 minute very generic exercises like Paper Tear, where the actual focus of the game on paper is of totally irrelevant to your real goal, but where it serves as a metaphor, over to several day, very detailed gaming experiences, which get into the precise coefficients of the system. I've tried to show where we're today on the overall scheme. So there's what I would call manual games. That's like Paper Tear. And all the other ones we'll be doing today. There are computer games. I don't need to elaborate on those. You know about them. Many are purely recreational, but the military uses computer games for training the military in useful combat exercises. Airlines use computer games for training airline pilots how to fly planes, and so forth and so forth. And then finally, there's role-playing games where people actually adopt the culture, norm, ethics, and values of some players and then work out their way through a solution. Manual games may take minutes. Role-playing games can go on for days and days. And because manual games are short, they're limited. We're talking today about ones which really just give you some idea about behavior patterns. There are ways to do that, stories and so forth. Not our concern today. There are, of course, many different types of games. Of particular interest to us in this workshop is the distinction between 3 different types. Mass games is where one facilitator, in this case, me, and any number of participants, in this case, you, can play out the game. So Paper Tear is a mass game. Mass games are great for Zoom because they don't require feedback and they can work with participants that are separated from each other. In demonstration games, you'll see a couple demonstration games in the videos that I'm going to use today. A small number of participants do the game, usually under the guidance of the facilitator, while others watch. And then the learning comes from discussing what it is that the participants observed during the demonstration. And then finally, participation games are where everybody in the room gets up and engages in one way or another in the process. Obviously, doesn't work very well under pandemic conditions. We can also usually talk about the difference between literal and metaphorical games. A metaphorical game doesn't obviously relate to any specific system. It generates an outcome that can be related to many common issues. It teaches a little about many systems. So paper terror is a metaphorical game. It's not in itself interesting, but as a metaphor it can be used in a very wide variety of circumstances. I've delivered workshops on limited growth, on agricultural systems, on energy systems, on making communities more sustainable. In every case, paper terror was a useful introduction because it showed the difficulty we were going to have when people talk to each other using ambiguous words. And a literal game is where you actually represent a system in some detail, the actual cause and effect relationships, the actual elements, the actual numerical variables are plausible for the real systems. And if you do it well, it can teach you an enormous amount about a specific system and a little bit about many other systems. I had a colleague who used to build literal games for companies where they had a particular problem. I remember a drug company, a pharmaceutical company wanted to build a new research facility in Europe. There were a lot of issues, tax issues, issues related to the treatment of animals in tests, salary issues, and so forth. And rather than trying to make the decision, they created a literal game. The senior executives came together for a weekend, played the game, and in the process figured out where to put their research laboratory. And of course, after they played the game once, it was no longer of any use to them because they'd already made the decision. They for sure didn't want anybody else to have the game because it had a lot of information about their company in it. So that's a literal game. So here's slide 21. Remember, we're going to stop in just a moment for questions. But before we do that, I wanted to issue a warning. Even if you're very, very successful with your games, giving people new understanding, it may not give you the behavior you want because there are two different ways that people think. In one, you decide which data you consider are important. You gather the data, do research on it. You begin to observe patterns. You form from those patterns hypotheses. And from the hypotheses, you derive actions which you should take in order to change the data. I am generally of that mode. I was trained as a scientist. My work has been in science. I generate data, hoping it's going to produce new action, and often being disappointed that it doesn't. And that's because there's a second mode of thought. Action leads to belief, leads to data. The climate skeptics are a wonderful example of this. I remember recently a dialogue down in Congress in the United States. One of the climate skeptics believes that big government is simply unacceptable and recognizes that any effort to control emissions is going to imply big government, more institutions, more regulations, and so forth. So that person starts from the knowing that the action of creating a big government is unacceptable. that leads them to deny climate. Whether they believe that climate is changing or not, it's irrelevant. They publicly deny it. And then they look around for data to justify the decision. And I remember explicitly the conversation that went on. I mean, so this skeptic said, there is no climate change. The polar bears are doing better than they ever have before in history. Well, some scientists went out and did studies on polar bears and concluded that actually they're in fairly desperate straits. So rather than changing their action, the skeptic simply changed their data. Well, I don't care really about polar bears. I don't believe there's climate change because it snowed in Washington, D.C. last week. You could, of course, do a lot of research to show that snow in Washington, D.C. is diminishing on average because of rising temperatures, present it, and the only result would not be new action, but that the skeptic would simply look around for more data. So with that, I'm going to pause and have a chance to meet you a bit more personally. I'm going to turn off my slides now and ask if we could spend some time talking about any concepts or questions I've mentioned that I didn't do a good job on, that you'd like some more explanation about, and so forth. And then we will rather quickly get off into a rather rapid fire demonstration of a bunch of different games. Varying time constants. This is one of the really, really serious comprehension problems in climate change. I remember I was asked by a museum director in Germany to help design an entire floor exhibit of climate change that people could go through in the museum to have a better understanding. And the conceptual problem that I had with my group was help people who could draw from a 15 or 20-minute exposure to the exhibits, could draw out ideas and understanding about the process of climate change, which unfolds, of course, over very long periods. I have an illustration here. This is CO2 emissions from about 2005 up to 2021. And you see CO2 is rising from 380 parts per million up to about 420 parts per million. As you all know, this is actually not a very high level of concentration for CO2. I have a CO2 meter on my desk. I'm looking at it right now. It's reading 508 parts per million. That in itself has no biological effects. The problem is that when you have that level, it changes the thermal balances. When you see this scale, it doesn't seem so difficult. But if you recognize that this box is part of this time series, this is CO2 levels 800,000 years before today's 765 down to the present. And we're right now in this little box. This doesn't seem so difficult, but when you see that we are twice what has ever been experienced in the last 800,000 years, it begins to give you some sense of the issue. And the question is, how can we help people put the current situation, the short term, into a better understanding? I've struggled with that. I came up with a game called Balancing Tubes. I'm just going to describe it to you because this is it's a math game, but it requires materials, and I didn't have a chance to put the materials out. If I were doing this in a workshop, I would, this is a paper tube made from rolled up newspaper, and I would just put one out on every chair. I didn't have a chance to do that. So you'll have to imagine what I'm talking about. You can imagine taking a tube of, for example, newspaper, and balancing it on your hand. Then imagine that there's two different spots. Here at the top, which really corresponds to long-term, and here at the bottom, which correspond to a short-term perspective. It's possible to manage this tube and keep it balanced if you stay focused on the long term. If you look at the short term, none of you, certainly not I, can manage to keep that tube upright. In the process of just a 2 or 3 minute exercise, everyone in the audience has an opportunity to feel the frustration of being unable to control something when they have the short-term perspective, but start to gain some mastery of it when they look at the long term. And balancing tubes is a way to do that. In the book, as with all the exercises, we talk about how to introduce this exercise, run it, and debrief it. Another math exercise helps to illustrate differing facts. I call it circles in the air. And I'm going to ask you to do this one with me. So all of you put up your thumb, just as I'm doing here. And make it so that when you look at it from underneath, it's going clockwise. So get your thumb going clockwise. And slowly, don't change direction, don't stop, bring it down to the level of your belt. And the question comes, is it going clockwise or counterclockwise? If you did it correctly, it's going counterclockwise. But the notion of clockwise is so dominant that many people find, maybe you did when you did it, that without thinking about it, they somehow change their direction so that they're still going clockwise when they look down. And that's because when we have facts or start to have an understanding about something, we get fixed on it. We see this problem in the United States right now. This is a current map of differences in precipitation. And what I'm living out here right now. I'm a gardener. I'm quite concerned by the fact that we're not getting much rain at the moment. Meanwhile, it's torrential flooding and drowning down here in the Southwest. And the Southeast and the Southwest is in the process of entering a biblical period of drought, something they haven't seen in thousands of years. Now, if you ask people whether, whether they're in a period of drought or flooding, obviously people will tell you something different. And the point is, as also with circles in the air, there's a difference between the event and how something looks at the moment versus the underlying process. Climate change is an underlying process which has been going on for centuries and will unfold in centuries in the future. It tends to be discussed in terms of current events, which makes it very difficult for people to comprehend each other, because the people who are talking about climate change out here are preoccupied with drought. People who are preoccupied with climate change here are preoccupied with floods. And when you start talking about what should be done, what adaptive measures, what et cetera, of course, the answers are going to be very different. That comes in part because we have different frameworks. And now I'm going to try an experiment. I'm going to clip a video from my Uppsala workshop on frames to illustrate differing perspectives. And I hope that the video and the audio will be clear to you. This will take about just a couple minutes.
Is that people look at it in different ways. You have some people who look through the perspective of economics, and other people who look through the perspective of ecology, or some people look through the perspective of here and now, and other people look through the perspective of over there later. And of course, when people look through different perspectives, they see different things. And when they see different things, they reach different conclusions. So I'd show you a little game that just illustrates this. Let's say that all of these people from the center over here, are focused on a very short-term, narrow perspective. And all of these people are looking at a broad, long-term perspective. Okay? And now we're going to make a frame for looking through. So make a little circle with your thumb and your finger. But you people who are looking just at the narrow, you hold your frame out here. And you people, you're holding your frame right up here. Okay? Everybody look at my right thumb. You're looking too close. You've got to put your framework further up. I know it's hard to see. Okay, look at my right thumb. Who sees my thumb moving? Who thinks my thumb is not moving? So notice, all these people think my thumb is moving. All these people think my thumb is not moving. Actually, this thumb is moving, this one isn't. If you have a broad perspective, you see movement. If you have a narrow perspective, you don't. Now, you can use this, well, it's totally stupid exercise, but it shows this importance between, for example, economics and environment. You can have totally reasonable people reporting what they see, but you illustrate with this simple exercise, they see different things. Economists, when they look at the world, see different things than environmentalists. You see, there's an English saying, seeing is believing, but that's not right. It's the other way around. Believing is seeing. You see the things you believe. And if you're an economist, you believe certain things, and you will see them. And if you're an environmentalist, you believe certain other things, and you will see them. And therefore, you can get into an argument. Even though being totally honest about what you see, totally well-intentioned, you can have an honest disagreement. And this little frame is a way to help people break that down and start talking.
So that is a game I use to, when I'm working with a group of environmentalists and economists, trying to help them understand that it's okay to believe different things because they're just looking at different things. And if I'm successful, then they become more open to understanding that just because somebody else makes a statement that they don't agree with doesn't mean the other person is stupid or uninformed. It may simply mean that they're looking at a different part of the system. Now I'm going to turn to something which is absolutely inherent in climate change, and that's the notion of exponential growth. Growth which builds on itself and becomes more and more rapid. It's a crucial issue, not only for understanding the problem, but for gaining some appreciation of what we can do about it. I know it's frustrating to get up every morning and see that results of what you've been doing don't seem to be adding up or accumulating. But exponential growth is like that always in the early stages. And although day after day, it seems like nothing is happening, in fact, the process may be doubling until finally it becomes very large. And to inspire people to be a little more optimistic about that, I've created this exercise called paperfold.
Another reason that we can have these climate problems is that very small things happen and they seem insignificant. And then suddenly they become very important. Like economic growth. You know, somebody said, well, what do you mind? Just I'm going to increase the oil production by a few percent, or the population is just going to go up by a little bit. And these small numbers don't seem to make any difference, but they're part of an exponential process. And rather quickly, exponential processes produce big numbers. So here's a little exercise I used to have. So here I have, actually, my bed sheet. But, so I'm going to fold it in half once, which doubles the thickness. Fold it in half twice. I doubled again. Fold it in half again. And again. 4 folds. After 4 folds, it's about 1 centimeter thick. Roughly. Okay? Now, of course, I couldn't do that with this, but suppose I folded it in half 29 more times. How big would it be? Oh, interesting question. Who thinks it would be between my hand and the floor? 4 times, just so 29 more times. How many? Who thinks it would be between the floor and the ceiling? Who thinks it'd be between from here to the moon? Wrong. Not anywhere close. If I folded it 29 more times, it would go from Boston to Frankfurt, about 5,400 kilometers. You can do the math yourself. Take 1 centimeter and double it 29 more times. And it comes, I've done it 85 times because I had to make sure the book was correct, you know, otherwise. If you fold it this, of course you can't, but you can double, imagine doubling 1 centimeter, double 1 centimeter, 29 more times. You see, 2 centimeters, 4, 8, 16, 32, 64, 128, 256, 512, 1,000 centimeters. That's only 10 more doublings. 10 more would be 1,000,000, and 10 more of that would be another 1,000,000. And that's fine. Okay. So the point is, very small things can quickly become huge. I picked this specific number of 33 doublings of 4 plus 29 because that's actually roughly the relation of the global population to Adam and Eve. If you double Adam and Eve 29 times, it gives you the current global population, which is a little over 7 billion. You know.
So, very trivial exercise. I lifted a pillowcase out of my Uppsala hotel to do that, but it is a concrete illustration of exponential growth, growing by a factor rather than by a constant amount, and illustrates how surprisingly the results can explode on you. Fortunately, this isn't only true for the problem, it can also be true for our solutions. And it's important to remember that when we are out educating, if we teach 2 people and they each teach 2 people and those people all each double the number who understand it, you're engaged in an exponential process. Exponential growth comes from what we call positive feedback. And in my modeling discipline, we represent positive feedback through diagrams of exponential, positive feedback loops. Just for your information, I've drawn the feedback loop, which applies in the case of paper fold. So, of course, the key issue is the thickness of paper. And that influences the amount which is added every time you make a fold. The arrow shows influence, doesn't show flow. It shows, you can read it, as the thickness of the paper goes up, the amount added per fold goes up. And this positive sign means that they change in the same direction. If you were to reduce the thickness of the paper, then the amount added per fold would go down. It'd still be a positive relationship. And as the amount added per fold goes up, the thickness of the paper goes up. This is a reinforcing loop. If you increase this, it propagates around to increase it further. That's why we call it a positive loop. Now, as I mentioned in my talk, and it's true generally, no exponential growth continues forever. Every exponential process has a limit, was of course the central message of our 1972 book. Sometimes the limits are very long in coming. but they're always there. And in this case, they come from the speed of folding. And of course, as the speed of folding goes up, the amount of thickness of the paper goes up. That's, again, a positive loop. But in this case, the speed of folding is controlled by the amount of added per fold. If this gets really big, the speed of folding goes down to 0. That makes a negative loop. So this is a negative loop, which finally means you have to stop folding the paper. The counterpart for this is easily found in many aspects of climate change. Take the ice cover feedback loop, for example. Once again, we're interested in temperature of the air. That's the surrogate we're using for climate change. As it goes up, melting of the ice goes up. But that means that the ice cover goes down. However, ice cover reflects heat. So if ice cover goes up, heat reflected from the Earth goes up, positive link. However, it's also true with a positive link. Ice cover goes down, which is what's happening now. Heat reflected back out from the Earth goes down. There's a more or less constant amount of heat coming into the atmosphere. If more or if less of it is reflected back out, then the temperature of the air goes up. So if less heat reflected from the Earth, negative link, temperature of the air goes up. This is a positive loop, which is causing the decline in ice cover. And wherever you have a positive loop, you would expect to see exponential change. Sometimes, as in the case of temperature, the change goes up. Sometimes, as in the case of ice cover, the change goes down. And we see it here. These are data from about 1980 or so, 1980, up to 2019. The average extent, minimum extent of Arctic sea ice in September. And you can see, although there's noise from year to year, obviously the trend is down and it seems to be accelerating. You would think that
you're writing
things
to the
of this sort
discussion thread. You're sending them to Julia and not to the one you want to send them to.
So somebody's talking.
On your writing.
Hello? Okay, so I will continue. So you would wonder, why doesn't this cause people to take action? And the reason is because of short-sighted decision makers. And here again, I'm going to show you a very brief video of a game called thumb wrestling, which is designed to illustrate the difference between short-sighted and long-sighted decision makers.
Another little game that illustrates this. This game is called thumb wrestling. In thumb wrestling, your goal is to get as many points for yourself as you can. You're all going to do this, and I'm explaining the rules. And Lois will come up to illustrate the process. So in just a moment, I'm going to ask you to turn to and find a partner. And over here, where you have 5, you'll have to be like 2 rows maybe, but it doesn't make a difference. In a moment, you have your partner and you lock hands like this to bring your thumbs together. And then, don't do it yet, I'm just explaining. You know, this is always a problem. People are so eager to play the games, they don't wait until they hear all the rules. Then I'm going to say go. And when I say go, you have 15 seconds to get points. And the way you get a point is by pinning the opponent of your thumb, pinching it. Okay. Thank you. Thank you. No, you did get a point. No, I can. Once you pin the thumb of your opponent, of course, you need to instantly let loose in order to get more points. If you just sit there for 15 seconds, that's only 1 point, right? So, okay. So just a moment. So get your partner. Ready, set, and each person counts their own points. Just remember how many points you got. Ready, set, go. Stop. Stop. Okay. Let's see how you did. Everyone who got 2 points or more, raise your hand. Put them down. Everyone who got 5 points or more, raise your hand. 10 points or more, raise your hand. 15 points or more, raise your hand. 20. Wow, this is amazing. So, could you must be really a champion. Could you stand up with your partner and show your technique? Go. Oh, just a minute. Okay, thank you. You got 15 that way. Oh, you didn't count. Okay. Most automatically assume if I get more points, I have to keep you from getting more points. But actually, in this game, the way to win is cooperation. That gives you the most points. And also in climate change, you know, if we can somehow figure out how to cooperate, we're all going to get more points. Now, an interesting question. With a big group like this, almost everybody.
So that wrestling exercise illustrates something which is absolutely at the center of the climate change debate. And until we get people to understand this, we really have little chance to make progress in reducing climate change problems. I'm going to show it to you in a slightly different way. It's the same, illustrating the same point. There are easy problems and hard problems that we confront. This is time, now, and the future. And for the purposes here, we're going to assume that up is better. So we're here now. This is our current situation. And this, it could be many things. It could be CO2 concentrations in the atmosphere. It could be how many kilos you weigh when you step on the scale in the morning. Could be your income. Could be the number of votes you get in the election, whatever. I mean, whatever, however you define success. We're here now, but we would like to be over here later. And of course, that means better. Later depends on the problem. In the case of body weight, this would be some months. In the case of climate change, this will be centuries. But the diagram applies in either case. For easy problems, you imagine there are two actions, action 1 and action 2. With easy problems, if you start action 1, it takes you where you want to go. And at the next point where you're assessing or evaluating the situation, you're better off. Action 2 is a serious mistake, but already at the next evaluation, it looks bad. It's generally easy for people to agree on action 1 in this case. Easy to achieve your goal, to solve the problem. Unfortunately, climate change isn't like this. Climate change is a difficult problem. Now, it's the same framework. We're here now. We want to be there later. Up is better. 2 actions, and we're going to evaluate in the mean, be on the way there. However, in this case, action 1, which is a disaster long-term, looks better in the short term. See, it's giving a better result. Action 2, which is what we really need to do to get where we want to go, makes things look worse in the short term. Now, here is where you can have significant difficulties in finding agreement between a short-sighted and a long-sighted person. With the easy problems, a short-sighted and long-sighted person are going to agree because in the short term it's better, in the long term it's better. But in difficult problems, in the short term it's better one way, but worse the other, and so forth. Until people understand this, as I said, we have little opportunity for solving climate change. And thumb wrestling is a way to do that. By focusing on the next point and struggling to pin the thumb of your opponent, you give up the opportunity of getting 15, 20, 30 points by staying focused on the long term. I'm going to demonstrate one more video, actually, and then turn it to a couple of math games and then stop for questions.
I discovered in a book a secret code. I'm going to use that code to tell you different numbers. And to make it simple, I will tell you numbers just between 1 and 5. 1, 2, 3, 4, 5. Even integers, no decimals. Very simple. So 5 different possibilities. Initially, when I show you the code, you won't understand what number I'm showing you, but quickly you will understand the code, and then I can use that code to show you numbers. Okay? What number am I showing you? I'm showing you 4. How many people thought I was showing you 4? Raise your hand. About a fifth, which is, of course, what you would expect. Random. Try it again. What number am I showing you? Don't say it out. I can form the number in your mind, and then I'll ask. But if you shout out a number, it's an interesting principle of game. If one person shouts out the number, everybody else says, oh, I don't have to think about it. And if they don't think about it, they don't make mistakes. And if they don't make mistakes, they don't learn. What number am I showing you? I'm showing you 1. Who thought I was showing 1? Oh, getting better. Try it again. What number am I showing you? I'm showing you 3. Who thought I was showing you 3? Oh, this is going backwards. Now I'm showing you 5. Now I'm showing you 1. What am I showing you now? 2. Great. The code is very simple, but you have to look outside the box. As soon as you don't permit me to bound where you look, you understand it very quickly. But if you let me restrict where you look with my box, you never figure it out. Sustainable development is like this. The politicians and the economists have made a box. And they tell us that inside that box, GNP and employment and stuff like that, those are the numbers we need to work with for sustainable development. Well, the answer to sustainable development is not inside that box, it's outside. Okay. So you see, now I've used this exercise with people who are designing new agricultural technologies.
That exercise is so powerful for people because it's simple and it confronts them with their own failings. As soon as you draw a square, it starts scribbling inside it. Everybody focuses their attention on what's inside the boundary. That's exactly what's happening with climate change. The economists are telling us that the solution to climate change is by imposing taxes on CO2 emissions, for example. Or the politicians are telling us that the solution for climate change is to shift over to renewable energy. Or the agriculturalists are drawing a boundary around agricultural technology and telling us that in order to deal with climate change, we need to change our practices with respect to fertilizer and irrigation and so forth. These are all wrong. In every case, someone is drawing a box and then putting inside it the variables that give them power, influence, profit, and telling you those are what you have to work with to solve climate change. In fact, the solutions for climate change come outside the box. They come from a shift in our understanding about the nature of our societal purpose, about the possibilities, about the role of technology versus ethics. Unfortunately, these are areas where many people have no profit interest or no possibility to exploit it for political gain. And as a result, they never draw the box around those factors. I find that when I want to get into a constructive discussion in my town, for example, about what we can do for climate change issues, playing that little game, Secret Code, hands down, is an extremely interesting tool for getting people to look more broadly at their possibilities. And when they start to look at possibilities and actions, I have to remind them, as I mentioned, you can never do just one thing. You have to think about the side effects of the policies you propose. And that brings me to the issue of interconnected consequences. Very simple game. I'm going to run it for you. I'll talk you through it. It's in the book. I hope it will illustrate this purpose. I call it the biodiversity game because I invented this game actually on the fly at a conference. A friend of mine was the Director General of the International Union for the Conservation of Nature, and she was running a global meeting on preventing species extinction and asked me to come up with a game that I could deliver at the beginning of the meeting to help people understand the nature of the problem they dealt with. And this is the game I came up with. I'm going to ask each of you to attend to what I say and do your best to answer my questions. Write down your answers so that you can compare them with the factual answers later. And it's by comparing what you guess or calculate with the reality is you begin to see where you're effective and where you may need to change your understanding. So here we have a set of triangles drawn inside another triangle. There are 9, if you count them, there are 9 small triangles here. 1, 2, 3, 4, 5, 8, 9, 9 triangles. And the question is, how many different triangles are actually formed when you put those 9 one on top of another? So I'm going to pause for just a moment and let you come up with a number. How many different triangles? Because of course there are the 9, but then there are more. For example, there's this really big one. The total makes a triangle. So that's already 10. And there are more than that. So how many do you see? Okay, I hope you saw 13. Here, I count them out for you. They're the 9, but then outlined in red is another triangle. That's 10. Here's another one. 11. And of course, this one on top, comprised 1, 2, 3, makes another. That's 12. The entirety is the 13th. So 13 different triangles are created when you put together 9. Just as very complex interrelationships are created in an ecosystem when you put together a few. But in climate change, we begin to break down the ecosystems, effectively removing triangles. So the question comes, if you remove one of the smallest triangles, then how many of the 13 will still be left? Take away one of these little triangles, remove all 3 of the lines which form it, and then ask yourself how many triangles are left. I'll leave you a few minutes to come up with a number. Well, the answer, of course, depends on which of the little triangles you remove. There are 3 generic possibilities. Of course, there are 9 little triangles, but they only occupy 3 different critical positions. And if you remove any one of those 3, you can replicate all the other possibilities. So here I've done that. To remove the top one, 9 triangles are left. So you go from 13 down to 9 by simply removing 1. 13 minus 1 equals 9 doesn't make sense in algebra, but it's a fact of life in ecological systems. Here, if you take out that middle triangle, you only have 6 left, 1, 2, 3, 4, 5, and the big one, 6. Or if you take out this triangle, you have 7. So you have this interesting fact that start with 13, take away 1, and you have the non-algebraic solution. Many people don't comprehend that. They think that if you take out a species, then in the ecosystem, only the number of species is reduced by only 1. We know that's not true. Climate change is extinguishing keystone species. And when that happens, there's a cascade effect, which can remove many others from our system. You can't reduce the number of triangles by only 1 because they are so interconnected. Species are actually more interconnected to each other than the triangles are. I noticed that in my own backyard. I have a garden. Ticks are an important problem in our garden because they bring Lyme disease. So I thought that I would get rid of the ticks. And you do that through a clever technique with pesticides. Indeed, I did eliminate the ticks, but I also eliminated several species of ground-dwelling bees because they occupy the area where I was putting the pesticides. And because the bees go down, the pollination in my plants is reduced, which is going to alter, not extinguish, but alter the frequency of those species. So when we come to talking about climate change, it's a serious mistake to evaluate its consequences, imagining that one individual species is going to disappear quietly by itself. Now I'm going to finish up with 2 quick math games, which illustrate the final problem I've dealt with in my communication related to climate change, and that is the unwillingness of people to change their habits. So I'm going to ask each of you to follow along with me. This is an exercise I've used with little school groups, with senior corporate executives, international officials, and so forth. And in every case, it generates some extremely useful insights. So please cross your arms. Everybody who's watching, cross your arms. And you'll notice, of course, that one of your wrists is on top. Now, some of you are going to say, I'll just watch. I'm not going to do this. But I'll tell you, if you don't do it, some of the important lessons are going to be escaping you. So I do ask everybody who's watching this video, please follow along. Cross your arms, look down, and see which wrist is on top. In my case, it's my left wrist. So for you, it's either your left or your right. Remember what that is. Now, drop your arms. Okay, now cross your arms again and look down and see which wrist is on top and remember it. Now, when I'm running this game with a group, everybody has the benefit of observing the other participants' experience, and that's helpful. In this case, we don't have that. I'm going to have to talk you through. At this point then, people cross their arms twice. They've remembered which wrist is up both times. And I asked the question, how many of you had the same wrist up both times? I did. I had my left wrist up on top both times. So I would raise my hand. Most people raise their hand. In a group of 50, I would say, generally speaking, 45 of them will raise their hand. People do tend to cross their arms the same way. Then I will say, okay, there's obviously an optimal method here since everybody's doing it the same way. Let's see what it is. How many of you had your left wrist up both times? And again, I raised my hand because I did have my left wrist up both times. But now I look across the audience and only about half the people are raising their hands. Oh, I say, how many of you had the right wrist up both times? And most of the rest raise their hands. So now we have a situation where everybody in the room, by and large, does it the same way, but half of them are doing it one way, and half of them are doing it the other way. And I explained that habits are like this. They are something you adopt to deal with common day situations. And you would be impeded and slowed down if you had to stop and think every time what to do. You fold your arms because you want to do something that doesn't require your hands. And it would be not very good if you had every time to stop and think, which way are you going to fold your arms? You adopt a habit, it works fine, and then you just quit thinking about it. Climate change is like that. We have adopted a set of habits about how we drive our cars, about how we heat our houses, about how we subsidize oil, about many things. And those habits are producing climate change. They're leading to the accumulation of greenhouse gases. And so I say to people, in order to solve climate change, we're going to have to change our habits. Now I'm going to give you practice. And now I'm speaking to you, all of you in this little workshop. Cross your arms the other way. I hope all of you are now trying to figure out how to get your other wrist up on top. Okay. When I do this with a large group, there's usually a lot of consternation and even some giggling because it's not easy to do it the other way. So I ask people to drop their arms and then I reflect on that and point out that this exercise shows several things. First, it shows that we have habits. We tend to do things the same way without thinking about them. But we can change if we set out to do it. Most of the people in the room are successful in crossing our arms the other way. There's always a few people who can't do it. However, you have to think about it. It doesn't come easily. It takes some time. And what most people experience when they're crossing their arms the other way, initially, there's a period of discomfort. It just doesn't feel as nice. And of course, exactly the same things are going to be the case for the actions we have to take with climate change. We can change what we do, but we're going to have to think about it. It isn't going to be easy, and some people are not going to be very happy about it, at least initially. And so drawing out those lessons is a useful way to make those points. And now I'm going to do one more quick exercise, and that will be the end of my formal remarks. And once again, I ask each of you, please follow along. Don't just sit there thinking you're going to watch eventually what everybody else is doing. Actually, I'm going to turn off my, okay. Great. So now I'm going to ask you to clap your hands in just a moment. I'll explain how to do that. I'm going to count to 3, slowly. 1, 2, 3. When I say 3, I want each of you, everyone who's watching, all 36 of you, 35 plus me, to clap your hands, all at the same moment. And then we will reflect on our success. If we're successful, and if we were all in the same room, somebody outside would hear one loud, brief, simultaneous noise. So just to repeat, in this exercise, your goal is to clap your hands all at the same time. And the way we'll do that, I'm going to count to 3 slowly. When I say 3, after I say 3, I will say clap. And precisely at that moment, when I say clap, you all clap your hands. Here we go. 1, 2, 3, clap. When I do this in a room, and maybe now in your own space, we observe that most people clap when I clap my hands, not when I say clap. There's an important lesson here. Actions speak louder than words. When there's a conflict between what I told you to do and what you wanted to do initially versus what I actually do, my words are not the same as my actions. You tend to pay attention to my actions rather than my words. And the same is true for climate change. As we gain understanding, we may identify new things that we should be doing. But unless we actually do them, all the nice words we speak about climate change aren't going to make any difference. Thank you very much. Those are my formal remarks. Now I will turn it back over to our host, who can express a few questions I may respond to. And then with all of you, I will gratefully give up these remarks and turn to listening to the many other interesting sessions in this workshop. Thank you.
Thank you so much, Professor Meadows, for this very exciting talk.